we are going to learn a theorem in linear algebra. A theorem on linear independence. Now, first of all, what do you mean by linearly independent set of vectors? If V is a vector space over a field F, a finite set of vectors are said to be linearly independent if a linear combination of the vectors equals to 0 implies each and every scalar in the linear combination is also 0. That is, alpha 1 v1 plus alpha 2 v2 plus etc. plus alpha n vn equal to 0 is a linear combination of vectors which imply alpha 1 equal to 0 and alpha 2 equal to 0 etc. alpha n is also equal to 0. So, if this condition is satisfied, then the set of vectors are called as linearly independent set of vectors. While using this condition, if any one of the scalar values, that is alpha 1 or alpha 2 or etc. alpha n is non-zero, then the set of vectors are called as linearly dependent vectors. So, first of all, linearly independent vectors means a linear combination alpha 1 v1 plus etc. plus alpha n vn equal to 0 implies each and every alpha I values equal to 0. Then the set of vectors are called as linearly independent set of vectors. Here this v1, v2 etc. vn belongs to the vector space V and each alpha I belongs to the scalar field F. Now let's move on to the theorem. Let S be a linearly independent set of vectors in a vector space V over a field F. Then every element of L of S can be uniquely written in the form alpha 1 v1 plus alpha 2 v2 plus etc. plus alpha n vn, where alpha I belongs to F. Now here it is given as S is a linearly independent set of vectors in a vector space V. We have to prove that every element of L of S, what do you mean by L of S means it is nothing but linear span of V. So linear span of V means span is also a set of a vector space in which each and every element is a linear combination of vectors. So if we consider L of S, each and every element in L of S will be of the form alpha 1 v1 plus alpha 2 v2 plus etc. plus alpha n vn. So in a vector space V, we can choose the elements as v1, v2 etc. vn. In any scalar, that is in a field F, a scalar can be chosen as alpha 1, alpha 2 etc. alpha n. But a linear combination, that is alpha 1 v1 plus alpha 2 v2 plus etc. plus alpha n vn is nothing but a linear combination of vectors which belongs to the span of V. We denote that span set as L of S. Now, in this theorem, they have given S as a linearly independent set of vectors over a field F. We have to prove that every element of L of S, that is the linear span, can be uniquely written as alpha 1 v1 plus alpha 2 v2 plus etc. plus alpha n vn, where each alphas belongs to F. Now, by definition of L of S, each and every element will be a linear combination. So let us choose alpha 1 v1 plus alpha 2 v2 plus etc. plus alpha n vn is equal to some beta 1 v1 plus beta 2 v2 plus etc. plus beta n vn, where these alpha i's and beta i's are all scalars belonging to F and v1, v2 etc. vn belongs to the vector space V. We have chosen two combinations. Alpha 1 v1 plus etc. plus alpha n vn is equal to beta 1 v1 plus etc. plus beta n vn. When we equate them, the right hand side is the linear combination of the vectors beta 1 v1 plus etc. plus beta n vn. When we bring the right hand side to the left hand side, the symbol changes from plus to minus, and then after grouping it, we get alpha 1 minus beta 1 into v1 plus alpha 2 minus beta 2 into v2 plus etc. plus alpha n minus beta n into vn, which is equal to 0. Now, the given condition is the set S is linearly independent set of vectors. So, linearly independent set of vectors means the linear combination equal to 0 implies the coefficient scalars is also equal to 0. So, using the basic definition of linearly independence, we get each alpha I minus beta I is equal to 0 for all the values of I. So, we get alpha I equal to beta I for all the values of I, which implies each and every linear combination can be expressed in a unique manner in the span of a set vector space V. So, the theorem is proved here. That is, every element in L of S can be uniquely represented as a linear combination of vectors. Then the next theorem. Any subset of a linearly independent set is also linearly independent. So, we are going to prove that any subset of a linearly independent set is also linearly independent. So, we have to choose a linearly independent set first and then choose a subset inside this set, and we have to prove that the subset is also linearly independent. Let V be a vector space over a field F. So, we are going to choose first a vector space over a field F, and then let us choose a subset S which is linearly independent. So, we are going to choose a subset S as V1, V2, etc. Vn, which is linearly independent set under F, under V. Now, let us choose another subset S dash of S. We have to prove that this S dash is also linearly independent. In opposite manner, let us choose this S dash as a linearly dependent set. We have to prove that S dash is linearly independent, but we are going to choose it as S dash is linearly dependent. Now, first, without loss of generality, we take S dash is equal to V1, V2, etc. Vk, where k is less than or equal to n, and suppose S dash is a linearly dependent set. By the definition of linearly dependent set, we can say that the scalar, some of the scalar values are non-zero values. That is the alpha I which belongs to F. Some of the alpha I values may not be equal to 0. So then there exists alpha 1 etc. alpha k in F not all 0 such that alpha 1 V1 plus alpha 2 V2 plus etc. plus alpha k Vk equal to 0. Hence, we get a linear combination as alpha 1 V1 plus alpha 2 V2 plus etc. plus alpha k Vk plus the remaining vectors till n can be represented as 0 Vk plus 1 plus 0 Vk plus 2 plus etc. plus 0 Vn, which is equal to 0. This gives a non-trivial linear combination giving the 0 vector. Hence, now it becomes S as a linearly dependent set because some of the coefficients from alpha 1 till alpha k are non-zero according to our assumption. This is a contradiction because in our statement it is given as S is a linearly independent set, but we get S is a linearly dependent set, which is a contradiction to our assumption. This contradiction arises since we have assumed that S dash is linearly dependent set. So, we have to change it. So, surely S dash will be a linearly independent set. Hence, a subset of a linearly independent set will also be linearly independent. Hence, the theorem is proved. Thank you.